Hello members, I welcome you back to my YouTube channel, and here we are to complete the lessons about benzene, and we are going to end with the chemical properties of methylbenzene, and we are going to find out that in methylbenzene we shall have a look at the reactions of the ring itself. Then after, we shall look at the reaction or the substitution in the methyl group. So there is substitution in the ring, then there is substitution in the methyl group, and then we also have the addition reaction. So like benzene, methylbenzene also undergoes electrophilic substitution reactions, only that the substitution can take place in two cases. We have the reactions in the methyl group, rather the substitution of the methyl group, then substitution reactions in the benzene ring, and then the addition reactions. So let's begin with the electrophilic substitution reactions in the ring. So basically, let's begin with the electrophilic substitution reactions as our first reaction. So basically, you need to know that these reactions, when you talk about electrophilic substitution reactions, they can occur in the benzene ring. We want to first see those electrophilic substitution reactions in the ring itself. In the ring itself. Remember what I told you in our video lesson number 4. We said that methylbenzene reacts with all electrophilic reagents, and in each reaction, it is more reactive than benzene. That one we made it clear yesterday, because we say that the methyl group donates electrons to the benzene ring, making it having a high electron density, thus making it easily to be attacked by the electrophiles. Yeah. So the substitution in the ring is easier than for benzene because of that reason that I've given you. The saturated methyl group is electron donating and thus activating the ring and making the attack occur in the 2 and 4 positions. So it forms the ortho and para products. So I will generalize all the reactions by doing one example of halogenation. But I want you to know that the rest of the reactions take place in the same way. So let's begin with halogenation in the ring. Halogenation in the ring. Now, as I've told you that this mechanism that we shall carry out, it is a general mechanism that will represent the rest of the reactions that would have taken place in the same ring. The reactions are not different from those of benzene, only that here we shall be forming a mixture of products. We shall be forming 2 isomeric products, that is the ortho product and the para product. So for example, for the case of halogenation, we shall be having benzene, rather methylbenzene, CH3, and we shall have chlorine with aluminum chloride, and we said we form a mixture of 2 isomers. We shall have methylbenzene here. We have an ortho, so we shall have a 2 substituted isomer and a 4 substituted isomer. So basically, this is what we form. Even if it is bromine, let me outline for 2, but we shall do 1, and I show you how the reaction proceeds. Then the rest of the reactions, you will follow the same trend. So if it is methylbenzene, and you treat it with bromine in aluminum chloride, you can use aluminum bromide, you can use iron 3 chloride, you can use iron 3 bromide, you form a 2 substituted isomer. We saw how we named these yesterday. So we shall form an ortho, BR, sorry, this is BR. Then plus, we shall form a 4 substituted isomer. I want us to see how the mechanism proceeds. Now, the mechanism of this reaction should be showing how all these two products are formed. You don't do the mechanism for one product. You do the mechanism for two products. So let's see what happens. We shall first carry out the mechanism for the formation of the two substituted isomer. Then after we carry out a mechanism for the formation of a four substituted isomer, but you can as well do them all together. But I don't want you to risk in doing wrong routes. So let's see how we can stepwise do this. Okay, so the mechanism. We shall have chlorine first. There are two chlorine atoms, and we have used aluminium chloride. So we shall have aluminium chloride. This will come first. I told you your arrow should bend once, and this will form chlorine, and then iron chloride as we shall form iron chloride. So this will be partially positive. This will be partially negative. Then I'll bring my methylbenzene. So I will bring my Cl, partially positive, iron chloride, partially negative. The electrons will attack the electrophile as this one goes off. Make sure that your arrows reach where they are going. Then after this, we shall have a plus here for electrons have left that side. Then here we shall have CH3. And we shall momentarily attach a Cl. The hydrogen will leave by stabilizing the ring. And you lose that hydrogen ion. And you will come to form CH3, Cl. That is how we form the two substituted isomer. I told you that you carry out for both isomers being formed. Some people prefer forming two isomers at this point, then they make the hydrogens leave at a go. But it's better to be safe. We formed for a two substituted isomer. So now you go to the formation of 4 chloromethylbenzene, chloromethylbenzene. The mechanism will proceed as follows. We shall have this methylbenzene. Then still you have Cl, partially positive. Then you have an intermediate, partially negative. This comes here. This goes, forming methylbenzene. You have this, you have that with a plus here. But remember, now we are going to form a 4 substituted isomer. So this is CH3. So since we are going to form a 4 substituted isomer, meaning our Cl will be on the 4th position, while the hydrogen now would be here. So this hydrogen will stabilize this ring here. And losing it will lead to the formation of our 4 substituted isomer, which is 4-chloromethylbenzene. For all mechanisms, whether it is alkylation, whether it is acylation, whether it is whatever mechanism, this is what you do. So you have seen that there is no difference between these mechanisms and those of benzene, but what changes is the positions where you're attaching the electrophile, or where which hydrogen the electrophile substitutes. So this is how the mechanism goes. You have to do for both isomers formed. So nitration, let me not find say that nitration, sulfonation, Friedel-Crafts acylation, Friedel-Crafts acylation, Friedel-Crafts alkylation, alkylation of the ring will occur by similar mechanisms as for benzene, forming the analogous products as for halogenation, meaning for all these ones, you'll be forming a 2-substituted and a 4-substituted isomer. So in all the reactions, the 4-substituted derivative tends to be a good yield, or it tends to be yielded in greater quantities, because it is a sterically more favored product. When I say a sterically more favored product, it means that there is no steric hindrance between the groups being attached. When I talk of steric hindrance, that's the bulkiness that may be the ring will experience as a result of the closeness of these substances being attached. But you see, a CH3 is here and a Cl is this side, so that there is low chances of having steric hindrance being experienced within this species. So that is it. For the rest of the mechanisms provided, it is methylbenzene, it'll be forming a 4-substituted isomer and a 2-substituted isomer. And that one brings us to the end of electrophilic substitution in the ring. Allow me to take you to electrophilic substitution in the methyl group, because that methyl group you've seen can also undergo reaction. So the reaction part B, we shall look at the substitution in the methyl group. Substitution in the methyl group. Substitution in the methyl group. Now, when you talk of substitution in the methyl group, this reaction will be proceeding through free radical mechanism, and it is similar to the substitution in the alkanes. So the moment we talk about substitution in the methyl group, think of the free radical mechanism. Think of the free radical mechanism. So the same way the substitution takes place in alkanes is the same way it will take place here. How? We shall have methylbenzene. And with this methylbenzene, it will be reacting with the chlorine. But then for easy cleavage of these chlorine atoms to form free radicals, we shall need UV light. And the product here, the product to be formed here would be CH2Cl2, because the chlorine atom has to substitute one hydrogen here. So when one hydrogen is substituted, we shall have CH2, then Cl. Then because we substitute one hydrogen, we shall have H. And because there is one Cl left, we shall have Cl. So this is what we call, here you've seen that the methyl group, rather the substitution has taken place in the methyl group. Now the mechanism will be following the free radical mechanism. So basically here we bubble chlorine through boiling methylbenzene in the presence of UV light or strong sunlight, and we form what we call chloromethylbenzene. So this compound we formed is called chloromethylbenzene. Interesting. Let's look at the mechanism. Someone who can remember very well from alkanes, the mechanism is very easy. The mechanism is initiated by formation of the free radicals, where we have Cl. Yeah. We shall have the fission. So in this case, we shall form two chlorine radicals. Now, on formation of the two chlorine radicals, now after forming the radicals, I'll bring my methylbenzene. So I will have, now this time round, we shall not have the bond reacting. So even if you use the one with the circle, because we shall not have the ring reacting. Yeah. So basically here I'll be having the CH2 and H, because it's supposed to be CH3. So I'm having CH2 and H. This is the same as CH3, but then I'll be having one chlorine radical. So what will happen is that here, since I want the hydrogen to associate with the chlorine to form hydrogen chloride, yeah, and I need a free radical on this carbon, I'll first form the free radical on this carbon. Then what will happen is that there will be a reaction between this chlorine and the H. So this one will yield, it will yield the CH2, free radical on C, then now plus HCl. Now, after I form this, now this free radical is the one that will react with the two radicals. So we shall have, I will be having I can write it as H2C, because I need the chlorine to associate with this to form CH2Cl. So now you'll bring in the two radicals here. You will have Cl, another Cl, yeah. So you'll have this forming a free radical here, and then this associating with this C to form chloromethylbenzene plus a free radical. Now, this free radical will interact with the remaining free radical, form the chlorine molecule. So this determination stage, we shall have the Cl plus Cl forming Cl2. So this is how this mechanism proceeds. Here we have substituted in the methyl group. Then we have one more last reaction. No, not last reaction. We have the oxidation of a methyl group, because in the methyl group, we can have this reaction with the, let me call it my reaction 1, this one that we've looked at, the free radical mechanism, let me call it reaction 1. Then now we are going to have the oxidation in the methyl group. This is the most important aspect in most of the synthesis reactions, yeah? So we shall see what really happens during synthesis of these substances. So basically, we have the oxidation in the methyl group. We want to see what takes place in the methyl group as a result of oxidation. So I want you to learn this. Oxidation in the methyl group. We shall just do a summary of this. Remember, oxidizing agents. For you to oxidize a methyl group, you must employ oxidizing agents. So in chemistry, we have strong oxidizing agents and mild or weak oxidizing agents. And as a matter of fact, let me first give you the strong oxidizing agents that we normally consider. Strong oxidizing agents. Basically, we normally consider acidified potassium dichromate 6 solution, acidified potassium dichromate 6 solution, which one can write as an ion, acidified. The moment you use this, the condition is you must heat. you must heat. We shall see what you form on heating. Another one can use acidified potassium manganate 7 solution. Can use acidified potassium manganate 7 or permanganate ions, but they must be acidified. And the condition is you must heat. Now, when you use this strong oxidizing agent, methylbenzene is converted to a carboxylic acid, and that is benzoic acid. So what I'm trying to mean is, when you use these strong oxidizing agents, the methylbenzene is oxidized to benzoic acid. So you have benzoic acid, but here we've said that you can use acidified permanganate and you heat. Or one can decide using acidified dichromate. Still you do heat. So if we use strong oxidizing agents, you form a carboxylic acid. But then we have got also mild. We have got mild or weaker oxidizing agents. So when you use weak oxidizing agents, you don't get the same product. For weak oxidizing agents, we are going to consider a number of them. One, we have acidified manganese for oxide, acidified manganese for oxide, and when you use this, the condition is that you will heat. We have also gotten chromium 6 oxide acidified, CrO3, and when you use it acidified, you must heat. Then we have also gotten chromium 6 dichloride dioxide. Chromium 6 dichloride dioxide. This one, when you're using this reagent, you don't put any condition. It is just used as it is. Chromium 6 dichloride dioxide. Or one can call it chromyl chloride. One can use it chromyl chloride. So when you use these mild oxidizing agents, now you don't get carboxylic acid, you don't get benzoic acid, but you rather get benzaldehyde or benzene carbaldehyde. You'll be getting benzaldehyde, that is CHO. So in summary, we can also summarize this. If you have methylbenzene, we say that we are going to benzaldehyde, CHO. So we can use acidified manganese for oxide. And you heat. Or you can use chromium 6 oxide, that is Cr, and you heat. Or you can use chromium 6 dichloride dioxide. You can use Cr or 2 Cl2. All these will give you the answer. Actually, you'll find out that as a note, you can note this for your own consumption. You'll find out that any alkyl chain on benzene ring other than methyl group on oxidation can form benzoic acid, as well as when you use acidified potassium permanganate solution. In other words, what am I trying to mean? I've said that any alkyl group on benzene, if you have like this, CH2, CH2, CH3, and you oxidize this, if you oxidize this using any oxidizing agent, acidified, and you heat, still you find yourself on benzoic acid. You need to note that for your own consumption. So this reaction is used basically to distinguish between benzene from methylbenzene, whereby the purple solution will be turning to a colorless solution with methylbenzene and no observable change with benzene, because benzene cannot be oxidized. So it means since benzene cannot undergo oxidation, I can use an oxidizing agent to distinguish it between benzene and rather to distinguish it from methylbenzene. For methylbenzene, a purple solution will be turning colorless, while with benzene, there won't be observable change. The final reaction is the addition reaction that methylbenzene undergoes. So if the addition reaction, this is what I'm finalizing with. Addition reaction. So for the addition reaction, basically, if you have, for example, methylbenzene, if you treat it with the hydrogen in nickel at 150 degrees Celsius, we shall form methyl cyclohexane. Methyl cyclohexane. So there is no bond, please. There is no bond, just methyl cyclohexane. So we shall have just CH3, methyl cyclohexane. So when you treat it with the hydrogen in nickel, we form methyl cyclohexane. So allow me do for you some synthesis problems. I'm going to do for us some synthesis problems, like 5, but very fast. I'll be very fast, and we see. Let's see some of the synthesis reactions that can happen. For example, let's see how we can convert ethene to benzoic acid. How do you convert ethene to benzoic acid? Ethene to benzoic acid. One day I will conduct a lesson and guide you on how we synthesize some of the compounds. But if we want ethene, this is an aliphatic compound, to benzoic acid, which is aromatic because of the benzene ring, it means that by all means, we need to first make sure that we produce benzene. So how do you produce benzene? The methods in which benzene produced, we saw that we can polymerize ethane. So can we convert ethene to ethane? Why not? Get ethene, H2C, double bond CH2. First react it with bromine in tetrachloromethane. Bromine in tetrachloromethane. This reaction will form 1,2-dibromoethane, which is CH2Br, CH2Br. After formation of this, you can treat this with alcoholic potassium hydroxide. So you can treat it with excess potassium hydroxide in ethanol, and we shall form ethane. So after you formed, here you must hit, After forming ethane, we shall polymerize this ethane. And for you to polymerize ethane, you can use complex organonickel catalyst. Complex organonickel catalyst. And use it at 60 degrees Celsius, or you can use 60 to 70, it is okay. This will give you benzene. Now this benzene can be converted to methylbenzene. Since it is methylbenzene that we oxidize, we shall oxidize the methyl, so we have to form methylbenzene. How do we come up with methylbenzene? We saw very many reactions. One can first convert it to bromobenzene, then you add chloromethane in sodium and dry ether, that is Fittings reaction, you form methylbenzene. Or you can do it right away by adding chloromethane and aluminium chloride. You find yourself on methylbenzene. Then you oxidize methylbenzene using an oxidizing agent. For example, I can use a permanganate, which is acidified, and I heat. This will give you your product benzoic acid. That is very easy for us. Then, what about how do we convert ethane to methyl cyclohexane? That one you will review. So how do you convert ethane to methyl cyclohexane? Still, this is very easy because we can convert ethane to benzene. I'm going to give you guidelines. First, convert ethane to benzene. You can use complex organonickel catalyst, or you can use iron. You can use copper at 600. First, convert it to benzene, then form methylbenzene. After forming methylbenzene, add hydrogen in nickel at 150. That one I won't do. This is for the viewer because I've given you the steps. So I want to see if you can manage. If you can't manage, please you let me know and we see what to do. Then we have, I want it to form benzene diazonium chloride from benzene diazonium chloride, benzene diazonium chloride to methylbenzene. To methylbenzene. This is very easy. Benzene diazonium chloride, this is a diazonium salt. We say that when you hydrolyze a diazonium salt, you can form phenol. Okay? If you have a diazonium salt, which we are talking about, N triple bond, NCl minus plus. If you hydrolyze this with the acidified water and warm, you find yourself on phenol, which phenol you can heat with zinc dust. If you heat phenol with zinc dust, it will be reduced to benzene. So you get your benzene. You get your benzene, and they want you to take it to methylbenzene. So from here, you can add substances that are taken to methylbenzene. You can add bromomethane in maybe aluminum bromide. You'll find yourself at methylbenzene. Alternatively, from here, you can go direct to benzene by adding hypophosphorus acid, H3PO2, in water. So you add the dilute or a solution of hypophosphorus acid, you take yourself to benzene and you take the process like that. Second last, we are just reviewing. Second last, we want to see how we convert bromobenzene, to phenylethanone. How do you convert bromobenzene to phenylethanone? So for you to take it to phenylethanone, there are very many ways you can take this. One, we first need benzene so that we carry out acylation. So how do we go about it? You have bromobenzene first. From bromobenzene, you can take it to methylbenzene by carrying out the Fittings reaction. I want every viewer to write the reagents in here. After taking it to methylbenzene, you can oxidize methylbenzene to benzoic acid using appropriate reagents. So to benzoic acid. From benzoic acid, you can decarboxylate using soda lime, or Sorry. Anyway, good thing you have to put the condition. So you do and get benzene. Now from benzene, you see the suitable reagent that you can add to get phenylethanone. Phenylethanone, COCH3, to get phenylethanone. Or else, you can still go to phenol. You can go to phenol from bromobenzene. I want you to see how to go to phenol. Maybe here I can give you a hint how to go to phenol. You can add steam in silicon at 450 degrees. You find yourself at phenol. Then from phenol, you can reduce to benzene the way we saw. I want you to complete that, all the viewers. Then the final one that I would want you to do, is the methylbenzene to benzene sulfonic acid. Methylbenzene to benzene sulfonic acid. Now, for this case, still you'll be putting reagents. You can have benzene. Methylbenzene. Can have methylbenzene. Methylbenzene, you can oxidize the methyl group, form a carboxylic acid, that is benzoic acid. From benzoic acid, you can decarboxylate with a suitable reagent to form benzene. Then from benzene, you can add a suitable reagent from benzene sulfonic acid. This is how I want you to practice synthesis. But I want you to put into consideration that one step that is wrong along the way can make everything wrong. I wish you the best. That's how we have brought to an end the reactions of benzene. But I want a viewer to practice this synthesis on your own without me giving you advice. I want you to see how to convert the following: propene to nitrobenzene, propene to nitrobenzene, convert benzene to polyphenylethene. I want you to convert benzoic acid to chlorobenzene. I want you to convert ethane to benzaldehyde. I want you to convert benzene sulfonic acid, benzene sulfonic acid to benzene carbaldehyde. I want you to convert ethene to phenylethanone. I want you to convert phenol to benzoic acid. I want you to convert methylbenzene from benzene sulfonic acid. Methylbenzene from benzene sulfonic acid. With these, I think we can move. There are very, very, very many other syntheses which you can do. But if you really need, if you feel like you need practice, you can send a message on that video. I will go through the messages. I will see how to assist you. I wish you the best.